Hello everyone, this is Dr. Anandan from the Department of Physics, Dr. N.G.P. Arts and Science College. Today I'm going to present the topic of SR flip-flop, D flip-flop and JK flip-flops. Okay, so these topics are coming under the course of Digital Logic and Circuits. So in this video, we are going to see the combinational and sequential circuits and what are the types of flip-flops, and we will also discuss on what is the SR flip-flop and their operation and the logic circuits and truth table. Similarly for D flip-flop and the JK flip-flop, we will also see the operation, logic circuits and the truth table. The digital logic electronics can be split into two different major circuits. One is actually combinational logic circuits and another one is sequential logic circuits. So one is actually it's a time independent circuit, the another one is actually time dependent circuits, which means the combinational logic actually depends upon only the current input. So you have an input and you will get a corresponding output. For example, adder, subtractor, half adder, full adder, you can take those circuits for examples of combinational circuit. Whereas when you go for a sequential circuit, actually this requires not only the current input but it also requires the previous input. So for that, to restore or to get the previous input, we need to have there is a feedback circuits like a memory element. Okay, so that actually stores the previous state and it will give the additional input to the current input, so that you will get the final output. For example, counters and all those circuits actually have are needed the previous inputs. So the sequential circuit, if you see, so this has a this has a primary inputs. The primary input that will go as a logical circuit, combination logic circuits, and you will get a primary output. But there is a secondary output that actually store a memory element. The memory element only we are going to see what are the memory elements. For example, flip-flops. Okay, so that actually gives back to the logic circuit as a secondary input, so that finally we'll get a primary output as the additional of primary input and secondary input. So this is how it actually sequentially working, and finally we'll get the primary output. Two types of sequential circuits are there. One is a synchronous circuit and another one is asynchronous circuits. The synchronous circuit actually work along with the clock pulse, which means the output will be changing according with the clock pulse. Whereas when you take a asynchronous, it actually work independently with the clock pulse. It does not require any clock pulse, but it uses the clock pulse, but it is not synchronous with the clock pulses. So this is the block diagram of synchronous and asynchronous circuits. So here you can see that in synchronous sequential circuit, the combination logic is there with the data storage along with the clock pulses. So this actually synchronous with the clock pulse. Whenever the clock pulse changes, accordingly the output changes. But whereas when you take asynchronous, it does not require any clock pulse or clock input, but it can work independently with but actually it has a feedback circuit, which means it takes some of the output as a secondary input. So we'll see once more the asynchronous sequential circuit, what are there in that. So these circuits do not use the clock signal but uses the pulses of the input. These circuits are faster than synchronous sequential circuit because there is clock pulse and change their state immediately when there is a change in the input signal. So we use the asynchronous sequential circuit when speed of operation is important and independent of internal clock pulse. In certain operations we use a asynchronous one. Okay. Similarly, synchronous sequential circuit actually uses the clock pulse, and according with the clock pulse only the final output will be changing. Okay, since they wait for the next clock pulse to arrive, they perform next operation. So these circuits are a bit slower compared to the asynchronous circuits. So similarly, the level output changes state at the start of an input pulse and remains in that same state until the next input or clock pulse. So we can see the forthcoming topics. We will see how this the synchronous is happening and all. So now we'll see the what is in the flip-flops. So flip-flop is a memory device. Simply, it is a memory device. It can able to store a single bit. The flip-flop is a another way it is called a latch. Okay, but depending upon the circuit combinations or clock pulse usages, it sometimes works as a flip-flop, sometimes works as a latch. It's a circuit that has a two stable states and can be used in a store state of information. Okay, a flip-flop is a bistable multivibrator. Actually, multivibrator is a signal generator. They have a three, you know already. It's a stable multivibrator that actually continuously generate the clock pulses, square wave clock pulses. Another one is bistable multivibrator that can have a two uh, stable states, and another one is mono stable multivibrator that actually has a single state. Whenever we give a trigger, so it will go to the second state and immediately it comes to the first state. Those are all three different type of multivibrator. So this flip-flop is actually working as a bistable multivibrator. So the circuit can be made to change state by signals applied to one or more control inputs, and they will have a one or two outputs. It's also basic storage element in sequential logic. As we have already discussed, it as a only single bit memory storage device. So this is the black diagram for flip-flop. So here you can see that there is a input for clock and there is a input the actual input is there, and there is a two outputs are there. One is actually called Q and another one is Q bar. So one is called a true output Q and another one is called a false output, that is a Q bar. So here you can see that and the flip-flop circuit is a special electronic circuit with the two output signals Q and Q dash, or it is simply another way it is called Q bar or Q dash, both are same. So Q output is being known as a true output and the Q bar is being complementary or false output. So these two should always be a complement to each other. So if Q is 1, then Q bar must be 0. Okay, if Q is 0, then Q bar must be 1. So this is how always it should be. If Q is high, then Q dash is low and vice versa. So if you take the two output stable conditions, then Q is equal to 1, then Q bar is equal to 0, and Q bar equal to 0 and Q is equal to 1. These are all called states. And we can also define that if when Q is equal to 1, this is called a set state, and Q equal to 0, then this stage is called a reset state. And now also we have to see how the clock pulses affects the flip-flop. So a clock pulse is nothing but it's a time varying voltage signal. Okay, depending upon two different states it occupies. One is zero state and another one, the high voltage state, is called one state. Okay, so when the clock changes from low state to high state, so this is called the positive going transition. You can see in the figure the arrow is given. So whenever there is a state changes from 0 to 1, so this is called a positive going transition, or otherwise it's called a positive edge trigger. So edge trigger means it can be only applied by variation of its state from 0 to 1. Similarly, the next the figure B shows the negative going transition, which means the clock pulse whenever it comes from one state to zero state, this is called a negative edge trigger or negative going transition. So these two different clock pulses are used in flip-flops and other sequential circuits. Okay. So the latches and flip-flops, they will have a same logic circuits, but it actually varies by using the clock pulses. Latch is a asynchronous bistable multivibrator circuit, and a flip-flop is a synchronous bistable multivibrator circuit. Okay. So here the block diagram, it is given two different circuits. One is actually acting as a latch, which means there is a clock input which actually enables or disables the particular chip, whereas In flip-flop, the clock is used to change the corresponding output. Okay, uh, with respect to the clock pulse only, the output, the Q is going to change. But whereas here, the clock pulse is used to enable or disable the particular chip. So what are the uses of flip-flops? So it can be used as a uh, it's a elimination switch, bounce elimination switch, and data storage, of course, and data transfer in intermediate states, and latches, registers, counters, frequency division circuit, memory device. Okay, so all are um, based on flip-flops. Now see what are the types of flip-flops available. So the simple first flip-flop is called set reset flip-flop, or simply called SR flip-flop. Okay, that those flip-flop can be made either by universal gates NAND as well as NOR, and we can also make a SR flip-flop with the clocked one, which means a clocked SR flip-flop, and we can also have a JK flip-flop, T flip-flop, D flip-flop, and a master slave edge triggered flip-flops. So all the major difference between these flip-flops are number of inputs and they have and how they change the states. Okay, these are all flip-flops, but each will be used in different purpose. So here first we'll see the SR flip-flops, which means set reset flip-flops. So SR flip-flops using NOR gate latch we are going to see, and SR flip-flops using NAND gate latch, and a clocked SR flip-flop, and S means it's a set and R means it's a reset. This slide shows the set reset flip-flop using NOR gate latch. So here you can see that first NOR gate is connected with the input of R reset input, and the output Q is connected to the input of the second NOR gate, and the set input is given to the second NOR gate. The output of the second NOR gate Q bar is taken into the input of the first NOR gate. So this is how the sequential circuit is given as a SR flip-flop. So here we can see the truth table. So when we have inputs of S and R as both are 0, which means the output is actually Q0, which means it's a previous state or there won't be any change in its output. Okay, and when we change the reset value as 1, so S is equal to 1, when we have a signal changes from 0 to 1, here we get a output as a 0 value, which means it's this is going to the latch, or the SR flip-flop is going to the reset state, or Q is going to 0 state, which means Q bar is equal to 1. And when we change S, the set as a 1, and R as a 0, reset as a 0, then we'll get a output as a NOR output in Q is equal to 1, so which means you will get a the final output Q is equal to 1, and this is called a set. But when we put the both input as a 1, so what will happen? So the final output will be, so when we have a both input as a 1 value, the final output will be Q as well as Q bar, both will have a value of 0. But this is not allowed according to the design of the circuit. We should have a Q bar should be always a complement to each other. So what will happen? So this Q bar state, both will have a same value. It is called a invalid state. So when S is equal to 1, R is equal to 0, then you get a Q is equal to 1. When S is equal to 0, R is equal to 1, Q equal to 0, and Q bar is equal to 1. When S is equal to 0, R is equal to 0, so which means the previous state, which remembers the previous value. But when we have a S is equal to 1 and R is equal to 1, this is a invalid state. So when we go to SR flip-flop using NAND gate latch, the same thing, but we have used the gate as a, instead of NOR we have used a NAND gate. So here it is the truth table alone is changing differently. You see both the inputs are 0, which means here it is a Q bar, both will have attain the same value, that is 1. So this state is not allowed in NAND gate latch. Okay, so other states are it's following in a little bit different I mean it is completely complementary to NOR gate. So when we see S is equal to 0 and R is equal to 1, we will have a value of 1 set. When we have a set value is 1 and reset value is 0, so here actually it becomes a reset, which means the Q value is actually becoming 0. So when we have 1 1, both values R and S will have a values of 1 1, then you will get the previous state, the earlier state what it was. Actually there is no change in Q. So this is how the NOR gate latch as well as NAND gate latch will be working complemented to each other in SR flip-flop. So here if you see S is equal to 1, R is equal to 0, and the Q values will be 0 and Q bar is equal to 1. Similarly, when we have a S is equal to 0, R is equal to 1, and the Q value become 1 and Q bar value become 0. So this is called the earlier state is called a set state, and the previous the Q1 Q is equal to 1 value is called a reset state in NAND gate latch. Okay, so similarly if both are 0, then this is an invalid state, because if both will attain a Q bar both will have the value of 1. This is not allowed because Q bar always should be complemented to each other. When we have a S is equal to 1 and R is equal to 1, so the Q and Q bar will have the previous state. So when we go to another flip-flop called clocked SR flip-flop, which means up to now we have seen it is only RS flip-flops alone. Now we will see the additional input is called a clock input. So this is the block diagram of the SR flip-flop with the clocked. So here we have given this arrow symbol which represents the edge triggered, positive edge triggered SR flip-flop. If there is a bubble inside, then it is called negatively edge triggered flip-flop. Okay, so there is no bubble, so it is clocked SR flip-flop. So here we have 4 NAND gates and combine together and make a clocked SR flip-flop. So here you can see the clocked SR flip-flop final output, the truth table of that. So here you see that both input are 0, so which means it attains the previous value. If reset is 1 and set is 0, so we will have the Q values as a 0. Similarly, when we have a set value 1 and the reset value 0, so here you have a set value, and 1 1 here again it is not allowed to state by using the NOR gate latch. Okay. So it is again the summary is given here. So for S is equal to R is equal to 0, the clock pulse is not applied. So when there is no clock not applied, then output of the flip-flop remain in the present state. So here the important point is we have to apply the clock pulse because it is given into the AND gate. So whenever we have to use a clock pulse, the AND gate has to work so that it is whenever there is a edge triggered, so by the time the input will go inside the flip-flop. So for S is equal to R is equal to 0 and the clock pulse is applied, then it will remain the previous state, which means Qn, if we take a current state, then Qn plus 1 is Qn plus 1 if it is a current state, and Qn is a present state. So for S is equal to 0 and R is equal to 1, then clock value is again 1 and Q is equal to 0. For S is equal to 1 and R is equal to 0, the clock is 1, then Q must be 1. For S is equal to 1 and R is equal to 1, both are same value and 1 value, and when there is a clock pulse is on, then these two are attaining the same value and this is not valid. And whenever the clock pulse goes back to 0, so there won't be any output changes in flip-flop. The next flip-flop is called D flip-flop, and this is another way it is called delay flip-flop, data flip-flop, or transparent flip-flop. And this is basically constructed basics of SR flip-flop, and the same RS flip-flop only here it works. But here only we have only 2 cycles, which means it avoids the intermediate states, which means when there is a combination of 0 0 and 1 1, it avoids. In order to get an invalid state, it avoids. So here you can see that the block diagram of D flip-flop. It has a single input, and with the NOT output it is going to the R state. So here it is nothing but a SR flip-flop. The S state is given input to the D, and the NOT gate, that is additional input, is given with the complementary input is going to the R state. So, and there is again it is a edge triggered clock input is given to the system, and you will get a Q bar 2 outputs. One is true output and another one is false output. So here you can see uh, the truth table. So this is the logical diagram for the T flip flop. It's already existing flip flop, but along with we give the NOT gate, so that it actually give the only 2 states. So when there is a clock pulse is on, then when we have a D value 1, so we'll get the value of Q becomes a 1. That is a set state. When there is a 0, then automatically this becomes a 1. So whenever there is a D value 1, then immediately there is a complementary input goes into the system, so that either you give an input as a 0 1 or 1 0. So first input is actually it's given 1, then it automatically becomes 0, so that we get output as a 1. So here we give a D value again, second value is 0, then automatically here the value is going to the second gate as a 1 value. So the final output value Q is equal to 0. So we get a reset state. So only we get either 1 state or 0 state. So we get a final output as a 1 or 0. So this avoids the intermediate states, the invalid states. Okay. So we'll go to the next flip flop called the JK flip flop. It is a refinement of RS flip flop. It has actually a clock input, and there is a J and K inputs, and there are 2 outputs Q and Q bar. So inputs J and K behave like inputs of S and R. Okay, so input marked J is for set and input marked K is for reset. If the inputs J equal to 1 and K equal to 1, the flip flop switches into the complement state. That means the Q is equal to 1, but it switches to Q is equal to 0 and vice versa, depending upon the clock pulse input. So here there is something called a new state is called a toggle. So which means Q bar always will be complementary, but whereas the value of Q will be completely changed. Whenever the J, K both are equal to 1, the Q output will have a toggle state, Q bar, but they should maintain the complementary final output. Here we will see how it changes. So this is uh, the logic circuit for JK flip flop. So here you can see that there is a AND gate, 3 input AND gate, and there is a input is given, K input is given here in first AND gate, and there is a clock input is a next input, and there is a feedback circuit from Q to the first AND gate. There is a feedback circuit is given. So these 3 input join together and make a final logic output here for S, for R as well as S. So here there is a NOR gate. Here we have used as a JK flip flop. Similarly, we can also use a NAND gate. So we'll see the truth table for this particular NOR gate based JK flip flop. So 2 AND gates are disabled when the clock pulses are absent. So here the first input clock pulses are not there, means there won't be any output. Okay, so no changes of state of output when there is no clock pulse. So when there is a clock pulse on, when you put a J equal to 0 and K equal to 0, both inputs are 0, so you'll get a Q output is equal to 1 and Q bar is equal to 0, that is initial values. Okay, or if you take these are all the initial values, then the same state will be retained, because j equal to 0, k equal to 0, which retains the previous state. And when we have a reset state, which means k equal to 1 and j equal to 0, on the arrival of a clock pulse, when there is a edge triggered, by that time you will get a q is equal to 1 and q bar is equal to 0. So therefore the rising clock it resets the flip flop. And when we have a j equal to 1, that is a set state, and k equal to 0, the state of flip flop changes to 1. And there is a new state is called a toggle state. It is happening in jk flip flop. So what is happening when j equal to 1 and k equal to 1? So then what is happening? So you will have a toggle state, which means depending upon the edge triggered clock input, the q output will be keep on changing. The first time it will be when it is attaining the value of q is equal to 1. The next clock pulse the value will become 0. So similarly, the q bar is immediately the complementary to q value, so that so the q and q bar always be a complementary state. Okay, so here you can see that possible to set or reset the flip flop depending upon the existing state of outputs. The output state of the flip flop is complemented, that is the important thing, and the change of state has occurred. The state will change each time the clock pulse arrives j equal to k equal to 1. So whenever there is a k equal to j equal to 1, depending upon the clock pulse changes, the q and q bar will be immediately change its states. If it is 0, then immediately it becomes 1, or if it is 1, it becomes 0. Okay, so that is depending upon the clock pulse. So here you can see uh, the truth label for the jk flip flop by using the NOR gate. So here j and k both are 0, and it returns the previous state. And when j equal to 0, k equal to 1, which means reset, then it is becoming reset 0 value. And when j equal to 1 and k equal to 0, you get an output value of 1 and it is set. And when j and k both are equal to 1 value, then the new state is obtained, that is a toggle state, and this q and q bar will be always complement to each other. So this is actually jk flip flop by using NAND gate. So previously we have seen a NOR gate, and here it is a NAND gate. By using the NAND gate, for the case 1, which means the clock pulse is 0, then there is no change. But when there is a clock pulse 1, clock pulse is still there, but the input j and k equal to 0, then again it retains the no change state. And when all the other states the clock is on, and when there is a k equal to 1, here it is reset, which means q bar is equal to 1 and q equal to 0. And when there is a j equal to 1, here again the q values as a 1 and the q bar values as a 0, that is again it is called a set state. So both are 1 will have a toggle state. So this is how the jk flip flop works. So in this as a summary, so we have seen what is in the sequential logic circuits, and we have also seen SR flip flop, and we have also seen what is clocked SR flip flop, and how the D flip flop is working, and how it avoids the one and the intermediate state that we have seen. And finally we have seen the refinement of RS flip flop or SR flip flop as a JK flip flop. There the complementary of the output is maintained in JK flip flop. Thank you very much.